So we've used kinematics to describe motion, and now we're going to talk about why motion happens through Newton's laws of motion. So Newton's first law, often you'll find it in a book, and it kind of sounds really weird, like if an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. Yeah, that sounds a little too general to make any sense. We physicists do that sometimes. So normally what I would do is dramatically lift the board and show you a better definition. But you know, things happen, things break, our boards are broken. To lift it now, I would actually have to have the strength to lift the entire slate board up in the air. And as we'll soon understand with our discussion of forces, I can't possibly do it. Maybe someday I'll show you how we really do it. It's broken, I can't lift it, so we're going to do it with a more sort of advanced way. Let's try this. This is the book's second attempt at a friendly first law. In the absence of external forces and when reviewed from an inertial reference frame, an object at rest remains at rest and an object in motion continues in motion with a constant velocity. That is, with a constant speed in a straight line. So this is still a little much. It sounds a little familiar though. You may have heard object in motion remains. And then what is this? We just did kinematics. You don't have to tell us what velocity is. No, I don't like this one. Again, I can't lift the board. Let's get rid of this one too. That's more like it. This is the one you memorized as a child on your parent's knee. An object in motion remains in motion, and an object at rest remains at rest. Since I'm a physicist, I do have to make it a little bit more complicated, not quite at the level we just saw. But let's make it clear, in motion means constant velocity. Like they said in the one definition, that's what in motion means. And an object at rest remains at rest. And we could add a quick clause, might help, unless acted on by an external force. And then it's pretty complete. You apply a force, this won't be true. What is a force? Let's think. A force is a push or pull. That's basically all it is. It's a mathematical description of a push or pull. We could make it a little more specific, that causes motion unless balanced by other forces. We could say that. By other forces. And we'll get into the math of this pretty soon. But we have to have the balanced part because right now I am under two forces and I'm not moving. I have a constant state of motion, I'm at rest. But there's a significant gravitational force pulling me down, but there's a normal force canceling it out. So next we're going to move on and treat these mathematically with the rest of Newton's laws. And now for Newton's second law. Yes, the great Isaac Newton, famous for saying, "If I see so far, it is because I stand on the shoulders of giants," which sounds very humble, but if you knew anything about Newton, he was not humble. And there's a theory that that quote was actually a dig on Leibniz, who was sort of his scientific competitor at the time and was not real tall. So forces accelerate objects would be my plain spoken simple definition of Newton's second law if I had to put it in words. Forces accelerate objects, but let's give it an equation because this is a physics class. According to the sum of all forces equals mass times acceleration. All right, let's start taking it apart and figuring out what everything means. So first of all, this is the fact that it causes acceleration. This is the same acceleration we learned about in kinematics. Any object can accelerate. This is what causes it. Acceleration, and we know from our discussion of kinematics that that is in meters per second squared is the unit, and we know that it's a vector. Okay. Mass, this is the first time we've seen mass. We didn't really have to deal with mass in kinematics because we were just describing motion. We weren't explaining it. It is the quantity of matter. All ordinary matter is made up of electrons, protons, and neutrons. They each have mass, so you sum up their mass and you get an object's mass. So that's what mass is, but it's also it also describes how an object resists motion. Since it's the constant of proportionality between F and A, then if you have a really big mass, it doesn't accelerate as hard. Right? So the more mass you have, the more it resists motion. What else we got here? We have the sum, and the reason here is there are different forces can apply at the same time. So you have to actually add up, vector add all the forces together, and their sum equals ma, not a single force necessarily. And then the forces are, of course, what we described before, the mathematical, now we're mathematical, pushes or pulls. And now you can see mathematically what I mean by a push or a pull, something that causes acceleration. Forces, you can probably now tell if mass is in kilograms, then forces are in kilogram meters per second squared, and we name this after Newton, right? In newtons, or abbreviated big N. So the MKS unit for force is the Newton. So this is the equation we're going to be using for at least the next week and on into the entire course. And now for Newton's third law, the great Isaac Newton, that cuddly teddy bear. This one is so well known. This one is sort of lyrical. Everybody learned it when they were a baby. When your parents bought you that CD of kids' science music, hoping it would like make you smarter later. This was somewhere on that CD they said this. You can even, as I start to write it, we're just all going to say it together. For every action, there is an equal and opposite reaction. Does that sound familiar? Way, way back, or maybe more recently. So the only thing I want to do this to sort of get it a little more physicsy is replace the old-timey word action with force here and here. And that's all we need to do. Other than that, it's in pretty good shape. But I want to tell you what this is really trying to say. Obviously, it's not mathematical. It's not like F equals ma. It's telling you something important that might blow your mind, okay? Forces are interactions between two objects. So for everything you're going to see in intro physics, it's always an interaction between two things. We could always describe it that way. That may not blow your mind so much, but how about this? Each object feels the same force magnitude. Force is a vector, it has a direction, so the two objects feel two forces, each one feels a force, opposite directions, but the exact same magnitude. This is very important for stuff we'll talk about later with conservation of momentum, blah, 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 but right now I just want you to soak it in, okay? All forces, any force you tell me about, I can tell you what the other force is. They're called action-reaction pairs. And later, once we talk about forces more, I'll show you how to find action-reaction pairs. But for now, I just want to see if I can convince you of this with a large, heavy pole. Here's a large, heavy pole. And here's a little handle. So what I'm going to do is I'm going to pull on it. Okay? Action-reaction pair. I'm pulling on the handle is pulling on me. Right? There's an action-reaction pair. When I take my finger away, I've got little stripes pushing into my skin so hard. Action-reaction pair. I'm pulling on it, it's pulling on me. But how do you know that they're equal? Let me show you. So what we're going to do is get these two scales, and just so you know I'm not cheating, I'm going to use two different scales. They're not even the same kind of scale, but they do measure force in newtons. Now I'm using two different scales. It has nothing to do with maybe the fact that I broke one of the scales. It's not that at all. It's that I want to show you the numbers. So now the scales are in between me and the pole. So they're showing you can imagine this is the force the pole is going to feel. This is the force I'm going to feel. And as I pull them, there's 10 and 10. Right? As I pull a little harder, there's 15 and 15. They're cheap scales, just get over it. And as I pull a little bit harder, there's 20 and 20. So no matter what I do, they always have the same force. So the action-reaction pair is always the same magnitude. Obviously opposite directions. I'm being pulled this way, it's being pulled that way.